In this video, we're going to describe a pathfinding AI that we've developed, and then we'll go ahead and talk a little bit about how it was coded. And to start us off here, we have John. You want to take it from here, John?
Sure, Stephen. In this lab, our goal was to use pathfinding and fuzzy logic to implement an AI. We had the freedom to develop the project as we saw fit, so we chose to create a game in Unity where the AI pursues after a goal, which in this case is a small plant, and avoids the player, represented by the knife. You can think of the game as being akin to golf, as in the lower score, the better. The objective of the game is for the player to kill the AI as soon as possible by intercepting it.
The game itself works on a 7x7 grid that was constructed within Unity. Each tile is given a value within the script in order for the AI to be able to pathfind between each node. Nodes that are unpassable, like the rocks, are automatically assigned a -1 value, while the other tiles are given a value depending on their distance from the goal, or plant in this case. There's also some negative values which are assigned dependent on the player's location, which helps the AI pathfind around or completely avoid the player in order to continue reaching the goal.
Thank you, Aaron. Now, the way the pathfinding works is first we do a depth-first search for the goal point. Then we gather the path that it takes to reach the goal point from the player, and we reverse the goal back to the player. At this point, we have a list of nodes connecting from the goal to the player. We reverse that list, so the first one is the player, and each sequential item in the list takes it 1 point closer to the goal. It travels this till it hits the goal. The goal point is then spawned in a new area, and a new list is created. However, this changes whenever the player or the enemy, the human player, gets close to the AI. When the human player or the enemy gets close to the AI, we do a different type of pathfinding. What happens is the enemy gives off a bunch of negative values in its general area. This lessens by each step. So -6 will be the first step, -5 will be the second step, -4 will be the third step, and so on and so forth. It assigns these values to each tile. The goal assigns positive values all around it. So it would assign maybe 6 from 1 step away, 5 from 2 steps away, 3, and so on and so forth. What the AI does then when the player gets close is it assigns all these values to the grid, and it picks the highest value it can find. If there are multiple high values of the same value, we then pick a random one from there. Usually we go for the one that is more open-ended. Then the AI will take that path, and if the player is still close, then it'll try to reevaluate the whole board again and decide the next best path, or it'll grab the highest value again. It will repeat this until it is far away from the player or the enemy, and then it goes back to the original pathfinding. That's pretty much it. I'm going to hand it off to Steven now, which is going to explain the fuzzy AI logic in order to achieve this.
So the final step of this project was to implement some decision making. We put in some fuzzy logic using a simple linear function for the calculation, instead of your typical Boolean logic, which uses just a 0 or 1, or an all or nothing value. Fuzzy logic will actually consider values that are in between. So a state can be more true than false, more false than true, or about even for multiple states. For example, if you're driving a car down a road and you need to stop, you don't want the brakes to be all on or all off. You would ideally want to make a smooth transition. And fuzzy logic allows us to do this. So with this linear function we use it to determine our chasing and evading states. And this is done by passing in 2 threshold values and the current distance between the AI and the player. If the returned value is above the larger threshold, the AI will be fully in the chasing state, and when below the lower threshold, the AI is placed fully into the evading state. But when the values are between these thresholds, it will perform a calculation and return values that we use for both states. So it will actually be in both the evading and chasing states. But whenever we do the comparison, we can see if the AI is in the chasing state more so than the evading state. And that allows us to make our decisions in hopefully a little smoother manner. But that's all we have, and this has been one of our AI projects for our CS373 class. Thank you for watching.